Hi, Assalamualaikum warahmatullahi wabarakatuh. I would like to replace our lecture this morning with this video. Galvanic cell is something that is new for you this semester. So we are going to have two beakers. Two electrodes is going to be dipped into the solution of its metal. Here, zinc electrode is on the left, copper electrode is on the right, and then it was connected with a galvanometer and also a salt bridge. So this is the basic diagram of a galvanic cell, which will produce electricity if it is connected correctly, and it will form spontaneous reaction. Let's look at the electron flow. There is from anode to cathode. There will be one question on the function of salt bridge. Salt bridge is an inverted U-tube containing solution of inert electrolyte. But the electrolyte KCl or sodium sulfate will not react with the reaction in the beaker. The function is to help maintaining electrical neutrality and to complete the circuit. This is cell notation or cell diagram where we have anode on the left, cathode on the right, separated by two lines in the middle, which represents salt bridge. Okay? And the reactant on the left side, which is zinc solid, will give away its electron through the wires, and that electron will be arriving at copper ion to make up copper solid. The thing is, if we are given two elements, we have to decide which element is going to become the anode or the one that is being oxidized. So we have to look at the table of reduction potential, where the copper that we have, for example, has positive 0.34. This is the E naught red. And for zinc, it is negative 0.76. This is the information given from the table, and in the exam we're going to give this in the question. So we have to look at a scale where 0 is in the middle, copper is over here, whereas zinc is here. So zinc has the least potential to be reduced, therefore it is going to be oxidized. If we are using the first formula to calculate the E naught cell, we are going to change the sign, reverse the sign of the E naught red for zinc, and we will get 1.1 volts. But if you want to use the second formula, we just insert the actual data from the table, but this is minus, so it's going to become the same value. You can use either one of the formula. Standard electrode potential can be measured by using the She standard hydrogen electron, because She has the value of 0. So if we put copper as cathode here, we put copper as cathode, and we know that the standard hydrogen electrode gives the value of 0, then the reading of the voltmeter would be the reduction potential of copper. So this is how we measure the standard reduction potential for all the half cell reactions in the table 2.4. Now the problem is if we are given that, for example, stannum is becoming the anode, will a spontaneous reaction occur? Will a galvanic cell formed? So we have to look at the reduction potential that is given in the question. Here it says that stannum has, this is 0, okay, this is negative 0.13. Stannum has a higher reduction potential. So if it is going to become the anode, we have to reverse the sign, okay, and then reduction happens at cathode, negative 2.38, meaning that this would give a negative value. If the anode cell is a negative value, it will not produce electron transfer, and the cell is not spontaneous. Okay, now this is correct answer. If we have a solution that is not 1 molar, then that would be considered non-standard conditions. Okay, she has to be 1 molar of hydrogen ion. If we use H2SO4, then if you want 1 molar of H plus ion, you can use 0.1 molar of acid, because 1 molar of acid is producing 2 molar of H plus. Kan? Okay, that is something that I wanted to share with you. But if HCl, you have to use 1 molar. If H2SO4, it is okay if you use 0.5 molar, because that would produce 1 molar of H plus. In order to use a She, you need to have 1 molar of H plus. Alright. Now, for Nernst equation, this is the actual formula. But since we have R is a constant, F is a constant, and the temperature is room temperature, so we can calculate and derive this 0.0592 constant, where log Q is the concentration of product to the power of the stoichiometric coefficient, and to divide by the concentration of reactant to the power of the stoichiometric coefficient. N is the number of electron involved in the half cell reaction. This is a question from the back of the chapter. Choose copper and argentum. Write half cell equation. So at anode, we have copper solid releasing its electron, 2 of them, to produce Cu2 plus aqueous plus 2 electrons. And then at cathode, reduction will happen, and Ag plus will receive 1 electron to become Ag solid. Now, if you want to produce an overall cell reaction, you need to multiply this by 2 because you want to eliminate the electron. So now we are going to write down the overall cell reaction. Okay. And then calculate the anode cell. Now, given in table 2.4, I think copper is 0.34, the inert red, and argentum is 0.80. So if you look at the scale, copper is having less reduction potential compared to argentum being an anode, because it is oxidized. Therefore, the sign would be reversed. Negative 0.34 plus 0.8. So the answer is 0.46 volts. So this is the E0 cell. Now, we're going to use this information into question C, where, okay, what's the Nernst equation? Firstly, E cell is equals to E0 cell minus 0.0592 over N. What is the product? Copper is X over this is the reactant. So the reactant is 0.7 to the power of 2. So solve for X, and you're going to get X as this is 0.45 given in the question. This is 0.46. Okay, and then N is 2. X is something that we want to find. So if you solve this, you're going to get X is equals to 1.067 molar. Now, explain how the cell potential would change if the concentration of copper is increased. If the concentration of copper is increased, you are going to perhaps replace X into 2, and you would find that E cell would increase. Okay, that you can test mathematically. And if you want to add a few sodium chloride crystal, NaCl will ionize to become Na plus and Cl minus, where Cl minus will react with argentum ion and it will form argentum chloride precipitation. Okay, and this will reduce the concentration of reactant, making the E cell decreases. That is how you explain question number D. Now, I am sure that you are familiar with electrolysis, as you have done a lot of exercises on it last year for molten and aqueous solution. The extra thing that we're going to learn here for this year is that for diluted NaCl solution is that you need to use the whole H2O as the species being discharged. So you're going to produce hydrogen gas and OH minus ion at the cathode. Water is selected compared to sodium because the E0 red for water molecule is more positive. So you don't need to memorize the ECS, electrochemical series, anymore. As in anode, again, water also has a lower E0 red, therefore it is going to be chosen to be oxidized. Therefore, the water is going to be discharged as well. The reaction involved is, okay, let's add together negative 0.83, and then the reverse of E0 red, which is E0 anode. Then we total them up and we got negative 2.06. Concentrated sodium aqueous solution would be 1 molar and above. 2 molar, 1.05, 1 molar, all is considered concentrated. So, water will be selected at cathode because the anode red is more positive. It's easier to be reduced. Okay. But at anode, we are going to choose Cl minus, even though the anode red is more positive because of the concentration. So here, even though the anode red is higher compared to water, it's going to be turned into negative 1.36 volts. So the anode cell will be negative 2.19. The power is supplied by battery for electrolysis. Now, let's look at two more questions from the book. 2 Faraday, okay, will deposit 40 grams of Y. Okay, given Y, the molecular mass is 60 gram. So, what is the Faraday involved? 3. Therefore, Y 3 plus is the ionic formula. Now, this is basically common sense because we know that whatever Faraday it is, it will become the same as the electron involved in the half cell reaction. Okay, now let's do the other one, electrolysis of molten barium chloride. Write the half cell equation. The half cell equation is Ba2 plus aqueous plus 2 electron become Ba solid. Okay, 1 mark. Write the half cell equation. How many grams of barium metal can be produced by supplying 0.5 amperes for 30 minutes? So we are going to calculate the Q, and I is 0.5 multiplied by 30 multiplied by 60. This would give you, where's my calculator, 0.5 times 30 times 60. Is it 900? Okay, 900. So 1 Faraday is 96500. Therefore, coulomb. Therefore, if you have 900 coulomb, that would be 900 divided by 96500. That would be 9.3232 times 10 to the power negative 3. Okay. All right. So now, 326 lah. Okay, 3 Now we want to convert this into Faraday. 1 Faraday is equals to 1 electron. So we are using 2 Faradays because 2 electrons is involved. Therefore, if 2 Faraday supplies 1 mole of barium sulfate, if it's 9.326 times 10 to the power of negative 3 Faraday, it will form, this is divided by 2, it will form 4.663 times 10 to the power of negative 3 mole. So what is the molar mass of barium? Let's look at the yellow page. Ba is 137.3. 137.3 multiply by that, and you will get 0.64 grams. So I hope this is the answer at the back. So Faraday's law is not that difficult, and you can tackle it however the question might come out.